My name is Pomorski. I'm also co-organizer of this workshop, and also I would like to give you some insight into my recent work associated with the development of quantum games and quantum algorithms. Well, still, it will be not that deeply quantum, but still there will be some attempt to build a universal bridge how to quantize classical game or classical stochastic game, where there is certain level of random factor present. So a kind of good example that was, I would say, it's a methodological example is a Conway Game of Life, which is commonly known deterministic game, and this work was done in direct collaboration with Kotula, that has already graduated. He has defended his Master of Science thesis with distinction, and yeah, just having 2 publications associated with his Master of Science thesis. Yeah, so, and this is also part of the activity of a quantum hardware systems company, and this work was done at when 2 faculties has been collaborating. Faculty of Computer Science and Telecommunication, Krakow University of Technology, and Faculty of Electrical and Computer Science, Krakow University of Technology. All right, let's move on. Yeah, so basically here you see examples of rules in classical Conway Game of Life. So basically the rules state that if a dead cell has exactly 3 neighbors, it comes alive in the next time step. If a living cell has 2 or 3 neighbors, it survives in the next time step. And if a cell has a different number of neighbors than stated above, it will be dead in the next time step. So there are simple rules. Example of system dynamics generated by student by direct Kotula is given below. And then in Conway Game of Life, we can, despite very deep simplicity of rules, we can see existence of many states. Some states are dynamically stable, and some are completely static, and some are unstable. So you see oscillators like blinkers, ships, gliders, guns, and so on. So some of the states which are given here, I would say, has some similarity to resonant states in quantum mechanics at some point. And it's interesting to see that, for example, those guys that go in this direction, you can even try to associate momentum principle with them, even though that in Conway Game of Life, neither momentum nor energy is preserved. But sometimes some of subsets have such type of kind of like feature. And basically what is also interesting, that there's creationism and annihilationism of cellular automata. So it's hard to consider this as direct physical system. Nevertheless, as we will see on the next slides, the methodology of statistical physics can be applied here and this is quite I would say effective approach of description of many cell systems, but with precondition that the number of cells is relatively big. So yeah, so basically it's also case of Markov process, and here how we mute. So usually in literature, the Conway Game of Life that was invented in the 70s has deterministic rules. But here what we do, we perturb deterministic rules, so we add some kind of noise like. And how does it look like in practical way? We add the probability of a cell state changing spontaneously regardless of its number of neighbors. So it can it can go into a life or dead state with a certain probability. And also second modification. So I'm now describing how to move from deterministic Conway game of life into stochastic Conway game of life. Second modification is a continuous mass that was introduced, replacing 0 and 1 mass, so like discrete mass, right? And then we have any dead cell having the total mass of its neighbors within a certain range has a certain probability of gaining mass in the next time step. That's how it is. And also any living cell having the total mass of its neighbors with a certain range has a certain probability of remaining alive or remaining dead in the next step. Sorry for whispering. Yeah, so that's modifications and how do they work in a practical way. So we have here the case of Markov process for if you consider one-dimensional Conway game of life, stochastic Conway game of life. So there is a sequence of probabilities how to emerge, how one state emerges into another one, and right. And now then so this is also example of modification of deterministic Conway game of life. So this structure as given here, it's a stable structure in the deterministic Conway game of life. So if you have such set of squares and that says in other areas, the whole system remains static over time. But then there's a probability of changing the state of a cell regardless number of neighbors, and then you can move next time step to different scenarios, and some of scenarios are depicted here. And then you can measure average death cycle of a population versus probability of changing of the state of a cell regardless of the number of neighbors, and that's how it is. So you see, after certain state has changed, I mean, from certain probability, for such size of square lattice, two-dimensional lattice with fixed boundaries, always the population is alive. So that's also some statistical observation that we have done. Then we have moved farther, and we have generalized the stochastic, well, the game of life for a single population of cells for n species of cellular automata. So and then we have imposed some kind of antagonistic rules among cells, which will be described on the next slide. So we just basically set cells distribution by forms of Gaussian wave packets, two-dimensional Gaussian wave packets in initial conditions, and then that's how dynamics is dealing with time. So actually, you can even try to think, because the rules are here quite stochastic, you can still try to map this problem, that is problem from kind of like statistical like physics to the kind of quantum language model in a way. Maybe I will just introduce the modified rules. And so here, the given mass at point xy at time t+1 at next time step is a linear combination of masses, but then there is different weighting number for different tribes, population, I would say. So in a sense, you have like competing nations somehow trying to propagate across the globe, and they have higher level of collaboration when they are within one group and lower when they're on the cross boundary. So you can translate this problem even to kind of like sociology or other, other sciences, let's say. So that's just to give you the flavor. That's how it is. Yeah. Okay. then finally we arrived to the point where we would like to see the maps of probability and try to use, because we have many macroscopic degrees of freedom, which at some point seems to be less relevant. So we try to formulate macroscopic degrees of freedom. And the first kind of puzzle we have faced was that, you know, we deal with a masses, a continuous mass of cells, and then there is questions: can you assign a kind of like energy to the system? And then, as initially I have indicated, then you cannot really assign the momentum to a cell, except very few cases. So definitely you cannot assign momentum, and there is no conservation of momentum. But still, at some point, because of there's maximum density of population, you can make a kind of equivalence of a mass and energy in first approximation. This is what we did. And then we simply took any book on thermodynamics, and we have introduced, we have used Gibbs thermodynamic entropy measure. And then there is ds is over dq over temperature, and dq is a heat or energy at some point. So here we make this equivalence that T is equal to dE over ds. And then later I would try to show some existence of thermodynamical cycles, but but this is the way of getting the temperature in classical stochastic Conway game of life. And at the same time, you need to know how to get entropy, and it's quite natural at this stage to use Shannon information entropy, even though you can think about any other measures, which is also part of the subject of future state. All right, and this is the languages and use and here, and the software platforms that has been used here for execution of simulation task. Python is in use, and then you can see certain chain of functionality. I think that's obviously you can represent this game by many other programming frameworks. All right. Then this is example of Dariusz Kotula simulator. So this is how it looks like from user perspective. Perhaps even we will try to introduce, maybe even to high schools or to some undergraduate courses, the simulator, as it's very good to, how to say, it's a kind of way to approach the physics from computer science, since those days computer science is more popular, but at some point deepness of view requires some physical tools, I would say. So that's quite nice and useful simulator, but obviously you have to master it by using that. And this is example of some so diffusion dynamics for unfortunately the strip is a little bit annoying, but that's how it is. So maybe I will. So we have the diffusion dynamics of two barrier system with two small holes in each barrier. So basically the case is that it's like in thermodynamics, we can have perturbative interaction of a systems by small holes. So here we have the cells replicate and start to take place in the first chamber, and then they diffuse to another chamber, and this is how mass is changing with time. And this takes this picture here takes 200 average simulation runs with 200 times steps. So here is the mass diffusion. So obviously, finally, certain maximum density is achieved because cells cannot exceed certain density due to overpopulation, right? That's how it is. So definitely there is a kind of diffusion process, but I would say it is a bit similar to diffusion process from the source, from unlimited source. So somehow you can see that outside this is injected into one of the chamber, and then it continues. Then entropy diffusion is also observed. Maybe I will remove this annoying. Yeah. So here we refer to the situation from the previous slide, and you see how diffusion does propagate. And then when you spot the dynamics of system with time, we have mass dependence versus time. It's called cycle. So mass saturates at some point. Actually, if you will squeeze the system, which will be shown later, you can decrease the mass. And then you get saturation of entropy. It is almost fitting the second rule of thermodynamics. Nevertheless, well, it's thus maximized, but I would say there's a certain origin of those peaks due to interaction with walls, initial interaction with walls. So I would say that second law of thermodynamics from observation is fulfilled approximately. And then how this temperature depends on time. So okay, so you can have a moving temperature average as given here. So actually, it's discovered that if system gets dynamical equilibrium, it always gets negative temperatures. Well, the concept of negative temperature also emerges sometimes in condensed matter physics, even though it's not that, does not often happen so much. If you don't use this temperature average, you get such temperature variations. So I would say the presence of positive temperatures is still rather signature that the system is not fully in dynamical equilibrium, that it equilibrates. At least that's simulation observation. And then you see how what's dynamics of total mass derivative with respect to time and entropy derivative with respect to time, how this dynamics is going with time. But of course, you see that entropy stabilizes, and also at some point temperature mass is also stabilized. All right, let me move on. Yeah, so we have various. Yeah, so then there's a case of a system and two walls are moving. As you see, you can have a kind of like thermodynamic cycle with a Conway Game of Life. And then obviously it's natural to ask what's the system temperature and entropy, and is it analogical to gas thermodynamics known from classical physics, statistical physics. And yeah, and the answer is rather positive. I would say the mass dependence and energy, so mass is equivalent of energy. So during squeezing, you have a mass and entropy behaving in a cycle way. And then also the temperature has cyclic property as well. And so this is somehow inherently not stable thermodynamically, I would say. And then we go for the next possibility. Since so far we have talked about relatively simple generalization of classical Conway Game of Life into classical stochastic Conway Game of Life. The next stage is trying to mimic quantum mechanics, and there are deep analogies between statistical physics, classical statistical physics, and the quantum physics. So we can try to. So the question was stated in that way: is there a chance we can mimic the quantum system behavior by certain generalization of stochastic Conway Game of Life? And in order to do it, since we have a concept of interference in quantum mechanics, we decide, and the concept of interference has also to do with waves. We have decided to introduce the phase, associate the phase to mass of a cell, of a living cell. So with each point on the lattice, we associate two real numbers, mass and phase, as you can see. So we have modulus of mass and a phase. And then we, in order to mimic a system somehow, quantum mechanics, which will be shown later, we have linear increase of phase dependence with time. As you can see, I believe there's supposed to be one here. This is some misprint. Anyhow, so the thing is, so all rules are the same, but the cell's edge and it's non-trivial dynamics of a phase. So phase has a consequence of okay. So there is this rule: the dead cell that comes to life in the next time step has mass and phase equal to, and there's this formula. So you considered 8 nearest neighbors for a given cell, and then that's how it is. And also phase, effective phase of the cell that emerges is also coming from the phases of neighboring cells. That's this type of rule that was introduced. And then it's instructive to let's say to see one-dimensional stochastic game of life, and I would say that okay, that we have a comparison of a system on the left side that has no phase dynamics, and on the right picture there is with phase dynamics, and then as you see that after a certain time, certain stationary behavior is obtained by. So you see that that's how it does run for the left system, and this is pretty flat, and for the right system is non-flat. And yeah, and then let's just move forward. So, and then there's an idea how to go further into quantum mechanics. So let's say, then the first thing that comes into mind having such simulation as before, so you do confirm from simulation perspective or even from intuition diffusion of mass, entropy, and temperature. And then it's quite natural to use a kind of second Fickle law. Of course, this equation, which is shown here, doesn't have to be that deeply. Well, we can have more other terms, but we expect a nonlinear diffusion in general case. So there's this certain operator diffusion coefficient that's not always the constant. So we have a certain operator equations for certain distributions which we consider. So that's a case of methodology for 1 and 2-dimensional systems. And then we have a quantum mechanics. So now the trick is how to generate a potential in a Schrödinger equation, which will result in dynamics of a probability map that we observe in a stochastic game of life. And first thing that somehow it's obvious to us is that the classical Schrödinger equation with real value potential has there's a preservation of there's normalization condition prefix. So if the Hamiltonian is Hermitian, the state normalization of state is preserved. In other words, the mass of a system is constant with time, and that's not the case of our system. So, and then since Hamiltonian operator generates eigenenergies that are real values, so Hamiltonian generates real eigenenergies, like that giving real eigenfrequencies in a resonant cavity, let's say. So if we engineer with this Hamiltonian in such a way that we add imaginary part of potential, then we can end up with complex value eigenenergies, which will be translated into complex value of frequencies. And if you have a book like Jackson, Introduction to Electrodynamics, in Jackson, you can account for a dissipation effect introducing complex value frequency. So here we will use this deliberately, the imaginary part of potential, for the purpose of playing with mass dependence with time. That's how it is. So we'll expect that this potential will have complex values, and the prescription will be quite simple. So basically, so you have diffusion. So you postulate this Fick law. So this is probability in terms of wave function. And then you conduct the calculations, which are quite simple, and you end up in such equation as given here. I will not go into all the details of this calculation. And finally, what you arrive is that your Hamiltonian in the quantum mechanics is related with diffusion and second derivative with respect to position minus h bar, this theta, which is phase dependence. So you can relate those two things. So let's say if I provide you the density map from Stochastic Game of Life, you can immediately build a Hamiltonian that so you can construct Schrödinger equation mimicking the same behavior. The open issue is this phase dependence, which I will discuss on the next slide. I guess it was not yet introduced. Okay, so it will be introduced on the next slide. Yeah, so in general, we have so again, we have a Schrödinger equation. We postulate that there's some dependence of potential on time that generates certain probability map with time, and then the prescription is that there are two terms of the potential that depends, so real and imaginary, that have such dependence. And then there's a question how to put this, how to get this theta, because I mean, we know that wave function is a square root of probability times e to the power e to the imaginary unit times theta. Question is, what is the theta? And my prescription is to go for a case of superconductivity and to go for the case of London equation. And then due to the certain postulated analogy, I can also prescribe the formula for a theta, but still you can, this is open argument. Okay, and simply saying, using this London equation analogy, the gradient of phase of theta is nothing else as velocity. So you can imagine how to intuitively introduce such measure. There's no one unique measure. Nevertheless, you can postulate certain class of measures. All right. So, and then this is how this potential was. Okay. So there is a mass distribution. So we already come back to the case of one-dimensional Stochastic Game of Life with complex value. And then we have a mass distribution in certain steps, as you can see. And then there's we can reproduce real value potential. So we see that somehow minimum of potential is localized here and here. And there are certain dynamics of potential with time that does reproduce this dynamics. So having these values of real and imaginary potential, you can try to build a quantum chip that will mimic the complex value stochastic Conway Game of Life. All right, let me move on. Yeah, and the same story can, okay, so before I have discussed this imaginary real value, then you have imaginary term. So obviously this imaginary term is responsible for creationism and annihilationism. Well, maybe I should stress one more thing. Here in this, so we have quasi one-dimensional problem in Stochastic Game of Life and also in Schrödinger equation, but in principle you can use also vector potential. I have not yet used it, so that's what you can do. Right, and then there's a question how to go deeper, because okay, so far we have shown the equivalence between, I would say, one-dimensional Schrödinger equation and complex value stochastic game of life. So this is somehow suitable approach for a single electron device. But we have used the formalism to describe movement of kind of electrons, like Schrödinger equation, which is a continuous equation. Well, there's still another way of doing that. It's a tight binding model. Okay, maybe this slide is a little bit not fully visible, so I will. So what's the story? The story is that you have, let's say, semiconductor nanowire, and then on the top there are the gates, and of course these gates, there's insulation in between, so they generate effective potential, and then the electron is trapped between area 1 and 2, but still can tunnel and so can move back and forth. So there's certain localized energy with presence on left side, right side, and there's some Hoping term. So that's called tight binding model. In one of my work, I described how to derive tight binding for Schrödinger, always under which circumstances is always possible. But what is important is that this tight binding model can be mapped to stochastic finite state machine. So if the presence of your electron here is so there's a probability that the wave packet stays inside this place. Of course, that depends on the barrier. And it's also the probability that the wave packet stays in the second place, and also there's probability of tunneling. So this framework, this tight binding model framework, is very well, you can translate it to finite stochastic state machine. But then, so one thing is the reality of a single electron devices that has very big potential for a quantum information processing because of high integration possibility. But on another way, you can play with this model. And then again, you have to violate natural parameters of usage of a quantum mechanics, since this Hamiltonian is Hermitian in general, if the one wave packet is preserved with time. But adding complex values to localized energy EL and ER and modifying to making this Hoping asymmetric, you can get non-Hermicity in this Hamiltonian, and then you can account for case of injection of wave packets or losing wave packets, let's say. Because naturally, there's a probability oscillation with time for a Hermitian case as given here. So the electron oscillates back and forth. All right, so then how to play deeper? So obviously, we still go even deeper into this quantumness of this Stochastic Game of Life. Now it's like the procedure is like semi-classical quantization that we have shown so far, and then so we have two-dimensional words, and then this is how this tight binding model can be rephrased. The problem is that this Hamiltonian does depend on the state, so it's non-linear case. So it's rather more desirable to go into kind of like Ginsburg-Landau equation, which is non-linear Schrödinger equation, than just Schrödinger equation. But still, we have some hints. So that the level of imaginarity, whether it's positive or negative, has to be regulated on the number of neighbors, and there is a certain function that is introduced here. So this is just example. So this is the kind of work in progress. That's how it is. And so we hope to get some more kind of dynamics of quantum cellular automata, and also it's quite expected that if we have a fighting tribes, we have certain level of quantum of entanglement if we try to translate the system to the quantum picture. Yeah, so there's still some other postulated Hamiltonians for a tight binding model, depending on the number of neighbors. So yeah, so that's this work, and yeah, actually, I got some suggestion from University of Warsaw to go for a D-wave machine, because this tight binding model has a lot of to do with the previous talk of Professor Gunatenko, that it's a kind of like spin-like model. So probably this quantum Conway Game of Life also can be implemented at IBM Quantum Experience. All right, and yeah, so there's a lot of results obtained by the already graduated student Dariusz Kotula, who is already Master of Science, person with Master of Science degree. So we have make a definition and simulation identification of negative temperature as a measure of achieving thermodynamical equilibrium. We have identification of continuous mass as effective energy of a system in the first approximation. Then we make identification of Shannon information entropy as effective entropy of the system. That at least this measure of entropy was used. And then we make a generalization of stochastic Conway Game of Life, introducing 4 species of cellular automata that accounts for a kind of like antagonistic relation or semi-antagonistic that we just prefer to be with one nation than with many nations, something like that. Then we have identification, we make identification of Game of Life mapping procedure from fixed second law to time-dependent Schrödinger equation. Then we use a tested thermodynamic concept in the game of Stochastic Game of Life with case of moving barriers. We get some even quasi-periodicity of certain quantities, so there is very rich nonlinear dynamics present there. We somehow approximately confirmed the second law of thermodynamics in the Game of Life, so even without preservation of mass and energy. And at some point you can approximately say that the Stochastic Game of Life is a bit similar to grand canonical ensemble somehow, from certain perspective. Then we, before the flatness of entropy was achieved, we identified some entropy peak that is also part of inherent part of system dynamics. Then we get a semi-classical quantization of Game of Life in case of one dimension by using this concept of dissipative Schrödinger equation. Yeah, we have introduced complex stochastic Game of Life as a way to mimic the quantumness of quantumness, and actually we have not yet managed to get interference patterns because we are searching for that. Well, still believe we can get it in certain way. And yeah, there was a formulation of Stochastic Game of Life using tight binding model. We have some other mathematical formalisms to which Stochastic Game of Life can be mapped, which are still analyzed by us. And we confirmed that obtained dynamics of Stochastic Game of Life by use of complex value Schrödinger potential. Yeah, and just wonder how much. Yeah, there is some literature, and well, I can say that probably we are one of the first in this field, so we need to rush with the new results to get more, to be more noticeable, I guess. It's very important to refer to this equivalence between finite stochastic machine non-dissipative and dissipative being binding Schrödinger model. It's my previous work, where I deal with this, because the first thing which I have observed was then having epidemic model. I observed that you can map it to quantum dynamics problem, having built in this kind of entanglement. So this was during this COVID time when I was analyzed. I was a bit interested more in epidemic model. Anyway, the second publication is underway, and yeah. And there are some posters, so you see some level of noise. So this is for the case of non-average case. So the simulator can produce various types of noises, which is also value by itself from that point of view. Yeah, and that's this paper, and I guess that's it. So thank you for your attention. So I would say that yeah, this is something very nicely. So this can be modified in many ways, and might have some broader importance. As I would say that yeah, I mean you can consider so here the automata, cellular automata cannot overlap. So different species. So one place can be occupied only by one tribe, but you can also make another version of that. So this will be a little bit like boson Fermions, a little bit like that. So